When we see a helicopter in flight, we are usually conscious of only one movement of the blades. That is, their circular or rotational movement. In actuality, however, there are 4 distinct movements or actions which are characteristic of rotor blades. There is rotation, of course, the movement of the blades around the mast. There is feathering, the movement of the blades around a span-wise axis to change their angle of incidence or pitch. There is flapping, the vertical movement of the blades, either up or down, from their established plane of rotation. And there is hunting, the leading ahead or lagging behind of the blades, from their normal position during their cycle of rotation. To see how each of these 4 actions contributes to the flight of a helicopter, we will examine them one at a time. The first of these actions is rotation. Rotation, of course, is caused by the engine operating through the mast, except in the case of auto-rotation. In any case, the effect of rotation is to create a relative wind. The relative wind is constantly changing direction in order to remain at a right angle to the blade as it revolves around the mast. Thus, the blade, during its entire cycle of rotation, is reacting to the relative wind to produce lift. Since it is lift which makes it possible for a helicopter to fly, rotation, then, is the basic movement or action of a rotor blade. Without rotation, all other actions of the blade would have no significance. But rotation alone is not enough. We also need some method of controlling flight. Any movement of the helicopter, either vertical or horizontal, is accomplished through feathering. Feathering includes any movement of the blade around its span-wise axis as indicated by the dotted line. Such movement alters the angle of incidence, or as it is sometimes called, the pitch angle of the blade, and changes the amount of lift which the blade will produce. Feathering is accomplished through either the collective pitch control or the cyclic control. Any change in the collective pitch changes the pitch of each blade of the rotor in the same amount through its complete revolution. This enables the pilot to vary the total amount of lift being produced and gives him vertical control of the helicopter. By increasing the collective pitch, he can make the craft rise. By decreasing the collective pitch, he can make the craft descend, up or down, as he chooses. A change in the cyclic control, on the other hand, increases the pitch of one blade and at the same time decreases the pitch of the other blade an equal amount. Therefore, it does not affect the overall lift which is being produced. Instead, it increases the lift on one half of the rotor disc and decreases the lift on the other half. This will cause the rotor disc to tilt in the direction of the lesser lift. And since a helicopter moves in the direction in which the disc is tilted, the cyclic control provides us with a means of controlling the direction of flight. Feathering of the blades, then, and the resulting modifications of lift provide us with both vertical and horizontal control of the helicopter. In directional flight, however, a helicopter is subject to what we call dissymmetry of lift. That is, a blade during the advancing half of its cycle of rotation tends to produce more lift than it does during the retreating half. The result is a tendency for the helicopter to roll over on its back. To combat this tendency, rotor blades ordinarily are allowed to flap. That is, they are allowed to move up or down as necessary in order to equalize the lift being produced by the advancing and retreating blades. Flapping is usually permitted in one of two ways. In the fully articulated rotor system, a hinge is placed near the root of the blade. This hinge permits the blade to flap up or down at will. In the semi-rigid system using two-bladed rotors, flapping is permitted by the teeter-totter action of the rotor head on its universal mount. One blade flaps up as the other flaps down. In any case, during flight, flapping is inherently limited by centrifugal force. That is, the amount a blade will flap up or down is a compromise between centrifugal force, which tends to hold the blade straight out from the hub, and lift forces, which tend to raise the blade upward. When the lift forces are stronger, the blade will flap up. When centrifugal force is stronger than lift, the blade will flap down. The net result of flapping is an equalization of lift between the advancing and retreating rotor blades. Thus, flapping overcomes the tendency of a helicopter to roll over, making directional flight possible. And this brings us to the final action or movement, which is characteristic of rotor blades: hunting. Hunting occurs only during directional flight and is the direct result of flapping. This is what happens. As the advancing blade flaps up, its center of gravity, which is indicated by the dot, is moved slightly nearer to the axis of rotation, which is the mast. Because of the Coriolis effect, this center of gravity attempts to maintain the same momentum which it had when it was farther away from the axis of rotation. In so doing, it tends to speed up the blade and causes it to lead ahead. At the same time, there is an opposite effect on the retreating blade. As the blade flaps down, the center of gravity is moved farther away from the axis of rotation. Because of the Coriolis effect, this center of gravity tends to slow down, which causes the retreating blade to slow down or lag behind. In other words, there is always a tendency for the advancing blade, when it flaps up, to gain speed and to lead ahead. In the meantime, the retreating blade, when it flaps down, loses speed and will lag behind. Lead ahead, lag behind. Lead ahead, lag behind. This variation in lead and lag during each cycle of rotation may amount to several degrees. To avoid the inevitable stresses which would result from this constant flexing of the blades, one of two methods is usually employed. In the fully articulated rotor system, a hinge is placed at the base of the blade. This lagging hinge permits the blade to lead ahead or lag behind as necessary. This is the method generally employed on multi-bladed rotors to permit hunting. In a semi-rigid rotor system, however, hunting is provided for in another way. The universal mount is designed so that it has a swinging or hammock-type action, which enables it to compensate for the lead and lag tendencies of the blades. In both cases, the provision which is made for hunting helps the blades to avoid the stresses which might otherwise result in fatigue failure. This completes our examination of the 4 characteristic actions of a rotor blade. In summarizing then, we can say rotation creates the relative wind which is essential to the production of lift. Feathering gives the pilot both vertical and horizontal control. Flapping enables the helicopter to escape the unpleasant consequences of dissymmetry of lift, but it also produces hunting. Consequently, provision for hunting is necessary to prevent the recurrent stresses, which would otherwise result from the lead and lag tendencies. While certain movements, then, may seem to make a greater contribution than others, helicopter flight as we know it today would be impossible if rotor blades were not able to perform each and every one of their 4 characteristic actions. In a helicopter, stability is one of the most difficult characteristics to achieve. There is an inherent tendency in most helicopters to roll or pitch, particularly in gusty air. To combat this tendency, a number of devices have been employed. One of the most successful of these devices is the stabilizer bar. This bar is fastened to the mast just below the rotor in a way which permits it a limited amount of teetering movement. The bar is set at a 90-degree angle to the rotor blades. The controls of the helicopter pass through a mixing lever in the bar before going on to the blades. As the rotor and mast revolve, the stabilizer bar revolves with them. Since the bar is weighted at each end and has no aerodynamic characteristics, it is influenced only by centrifugal force and by its gyroscopic properties, and herein lies the secret of its usefulness. As anyone who has ever spun a top must have observed, a spinning body tends to retain its relative position in space. It strongly resists any effort to change the attitude of its axis or rotation. In other words, spinning bodies possess a property which is common to all gyroscopes, the property known as rigidity in space. No matter how the mount is turned or tilted, the axis of the spinning gyroscope continues to point in the same direction. Since the stabilizer bar is in all important respects a gyroscope, it also possesses the property of rigidity. It is this property which enables it to increase the stability of a helicopter. The stabilizer bar, because of its gyroscopic property of rigidity in space, prevents a temporary disturbance of the rotor from seriously affecting the attitude of the fuselage. Also, it prevents incidental rolling or pitching of the fuselage from being passed on to the rotor. This stabilizing ability of the bar can be better understood, of course, once we know exactly how the bar influences the rotor. The rotor hub is secured to the mast by a universal mount called a gimbal ring. This mount permits the rotor to be independent of the attitude of the fuselage and mast. It is subject only to the controls which come from the swash plate. However, since these controls pass through the stabilizer before continuing on to the rotor blades, the bar is given a limited amount of control over the rotor. This is the way it works. From the swash plate, the push-pull tubes run to the inner ends of the mixing levers, which are housed in the stabilizer bar. The other end of each lever is pivoted to the bar. Then from the center of each mixing lever, pitch change links run to the control point of the pitch change horns, which in turn control the feathering of the main rotor blades. The turning rotor produces the rotor disc. Now, if a sudden gust of wind strikes the rotor blades, it may succeed temporarily in altering the attitude of the rotor disc. But any resulting movement of the controls will be absorbed largely by the stabilizer bar as it resists displacement from its normal plane of rotation. The bar will store up the movement and then dissipate it slowly as centrifugal force causes it to return to its normal plane of rotation, which is 90 degrees to the mast. Let's look at that again. As the gust forces the rotor disc out of its normal plane of rotation, the stabilizer bar exerts its counteraction. By feathering the rotor blades, it increases the angle of incidence on one blade as it decreases the angle of incidence on the other. By this feathering action, the rotor disc is returned to its normal plane of rotation, and a balanced condition will again exist. Likewise, if the fuselage for any reason is made to roll or pitch, the stabilizer bar, by retaining its same attitude in space, forces the blades to feather so that they too remain in their same plane of rotation. This prevents the momentary disturbance of the fuselage from being transmitted to the rotor. In a similar manner, any change in the cyclic pitch made by the pilot is modulated by the stabilizer bar before being passed on to the blades. As the rotor disc is tilted and the mast tilts along with it, the stabilizer bar assembly stores up some of the change which the pilot applied, and it pays it out slowly as centrifugal force causes the bar to resume its normal position, 90 degrees to the mast. The stabilizer bar then tends to slow down or modulate any sudden changes in the rotor disc, whether they are caused by the pilot or by exterior forces. In this way, the bar definitely improves the stability of a helicopter. However, to achieve this stability, a certain amount of the pilot's applied control is delayed. In an H-13 helicopter, only 71% of the control applied by the pilot is transmitted immediately to the rotor, and 29% is stored and then paid out by the stabilizer bar in from 15 to 20 seconds. If nothing were done to compensate for this lag of 15 to 20 seconds, there would be a serious lack of sensitivity in the controls. They would operate like this. The pilot, by changing the cyclic control, would cause the blades to feather. The associated tilting of the rotor disc would result in directional flight. The mast would tilt, but the stabilizer bar would tend to remain in its same plane of rotation, and it would be 15 to 20 seconds before centrifugal force was able to realign the bar in its new position 90 degrees to the mast. Since the bar has delayed 29% of the cyclic control, it would be 15 to 20 seconds before the pilot got a full 100% response to his applied control movement. And the same delay would occur each time the pilot moved the cyclic control. Obviously, the controls would be much too sluggish. In order to speed up the realignment of the stabilizer bar and increase the pilot's effective control, hydraulic dampers are added. The damper assembly is rigidly fastened to the mast just below the bar. It consists of 2 hydraulic dampers, each connected by an arm and rod to the stabilizer bar frame. The dampers work like this. When the mast is tilted in directional flight, the damper assembly is tilted with it. Since the stabilizer bar tends to remain in its same plane of rotation, the dampers immediately exert pressure on the bar, causing it to realign itself with the mast in 3 to 5 seconds. Since any disturbance affecting the rotor or fuselage would rarely last more than a few seconds, we suffer no effective loss of stability, and the dampers give the pilot greatly increased control. The stabilizer bar, then, because of its gyroscopic property of rigidity in space, is able to modulate sudden changes in attitude of either the rotor or fuselage. With the aid of the hydraulic dampers, it becomes possible to use the stability-improving characteristics of the bar without sacrificing any appreciable loss of control. Thus, the stabilizer bar becomes one of the most successful methods of increasing the stability of a helicopter. Today, when we see a helicopter rise gently from the ground, hover gracefully for a moment, then move off easily in directional natural. But it was not always so simple. The early designers of helicopters encountered many difficulties before they were able to get one of their craft off the ground. And they had still more difficulties to overcome before they were able to control its flight. One of their major problems was dissymmetry of lift, which means simply that in directional flight, rotor blades always tend to exert more lift during the advancing half of their cycle of rotation than they do during the retreating half. The result, of course, is an unfortunate tendency for a helicopter to turn over on its back. The cause of dissymmetry of lift is fairly simple. Lift, as we know, is produced by the passage of air over an airfoil. The air passing under the airfoil is compressed, forming a high-pressure area. The air passing over is accelerated, forming a semi-vacuum, or low-pressure area. This results in the creation of the force called lift. The faster the air passes over the airfoil, the greater is the lift produced. All other factors being equal, lift will vary as the square of the velocity. In a helicopter, of course, the rotor blades act as airfoils to produce lift. And the faster the air passes over the blades, the greater is the lift which is produced. Now suppose the rotor of our helicopter is revolving so that the tips of the blades are traveling at a speed of 350 knots. During vertical flight, of course, the blades will produce the same amount of lift at all times, since the air will pass over them at the same speed during their entire cycle of rotation. But the moment the helicopter starts to move in any direction horizontally, a dissymmetry of lift is produced. That is, the blade advancing through the unshaded area will begin to produce more lift than the blade retreating through the shaded area. If the helicopter is moving forward at 50 knots, then the tip of the advancing blade will be moving through the air at 350 plus 50, or 400 knots. Likewise, the retreating blade will be moving through the air at 350 minus 50, or 300 knots. Since the lift produced by an airfoil varies as the square of the velocity, it is apparent that the lift produced by the advancing blade is considerably greater than that produced by the retreating blade. And this dissymmetry of lift, if nothing were done to counteract it, would soon result in the helicopter turning over on its back. In order to prevent this from happening, some means must be employed which will permit the advancing blade and the retreating blade to produce equal amounts of lift. In most modern helicopters, this is accomplished by flapping. The advancing blade is allowed to flap up, while the retreating blade is allowed to flap down without changing pitch angle. If the advancing blade were not allowed to flap up, it would follow this path, and the relative wind would be from this direction. However, when the advancing blade is allowed to flap up at a high angular velocity, there is a change in the direction of the relative wind. This new path taken by the blade through the air results in a smaller angle of attack. A smaller angle of attack results in a reduction of the amount of lift. Thus, simply by allowing the advancing blade to flap up, we reduce the amount of lift which it produces. It is this difference in the relative wind caused by the flapping action which reduces the amount of lift. Meanwhile, on the other side of the helicopter, we increase the amount of lift produced by the retreating blade. Let's see how that is done. If the retreating blade were not allowed to flap down, this would be its path, and the relative wind would be from this direction. The relative wind is always opposite to the rotational path of the blade. Now, as the retreating blade is allowed to flap down, there is a change in the direction of relative wind, which results in a larger angle of attack. It is this difference in the relative wind, caused by the flapping action, which increases the amount of lift. Thus, by decreasing the amount of lift produced by the advancing blade and increasing the amount produced by the retreating blade, the two sides are brought into equilibrium. In fully articulated rotor systems, freedom to flap is made possible by a hinge near the root of each rotor blade. In the semi-rigid type of rotor system, freedom to flap is made possible by the teeter-totter action of the rotor head. As one blade flaps up, the other flaps down. Since the forces involved cause one blade to rise by an amount equal to the fall of the other, the seesaw mount or semi-rigid rotor construction poses no problem. No matter which mechanical means is used to permit the flapping action, the blades will follow the same path and produce the same result, an equalization of lift. Now, by the use of the cyclic control, the pilot can vary the amount of lift produced by the advancing and retreating blades, and can change the attitude of the rotor disc at will. By changing the attitude of the disc, he can maintain the desired attitude of the helicopter. Dissymmetry of lift, then, is prevented by changing the angle of attack of the rotor blades to equalize the lift produced. And it is only when this has been accomplished that a helicopter is able to fly with stability in directional flight. Do you ever wonder why a bird is able to fly long distances without flapping his wings? It's because he knows his aerodynamics. He knows instinctively how to locate an updraft and may soar for hours by making efficient use of aerodynamic forces. He knows that in order to gain altitude or soar in a given direction, he must have a suitable angle of attack, even though his attitude remains in an almost constant nose-down or beak-down position. However, man wasn't born with built-in flight instincts, nor did his mother teach him aerodynamics. Since that part of your education was neglected, we'll try to supply it in part. First of all, it is necessary to understand the factors which give you lift. In general terms, lift equals angle of attack times density of the air times area of the wings times velocity of the airfoil through the relative wind. Of the four factors which give you lift, the pilot can control only two: angle of attack and velocity of the airfoil. In a helicopter, the velocity of the airfoil results basically from the rotation of the rotor blades. A rotor blade is a wing or airfoil which flies in a circle, thus the term rotary wing. The chief characteristic of rotary wing flight is that relative wind and resultant lift is created by the rotation of airfoils through the air. In other words, the rotary wing performs the same function for a helicopter as a fixed wing for an airplane. The only difference is that in order to produce lift, a rotary wing flies in a circle, whereas a fixed wing moves forward through the air. Whether a helicopter is in flight or at a hover, the pilot maintains a constant rotor RPM. Therefore, the way he varies lift is to vary angle of attack. To understand lift fully, however, you must understand not only angle of attack, but also angle of incidence, which is sometimes called pitch angle. On a fixed-wing aircraft, the angle of incidence is determined by the relative position of the fuselage and the wing. The angle formed by the longitudinal axis of the aircraft and the chord line of the wing is the angle of incidence. The chord line of a wing is an imaginary straight line extending from the leading edge to the trailing edge. For our purposes, it is used to measure angles in reference to the wing. On a fixed-wing aircraft, the angle of incidence cannot be changed by the pilot. This leads us to the one essential difference between angle of incidence on a fixed-wing aircraft and on a helicopter. We can see this difference by observing non-rotating blades. In a helicopter, the pilot is able to increase or decrease the angle of incidence either by moving the collective pitch control or by moving the cyclic control. Now let's take a closer look at rotor blade angle of incidence. In broad terms, a rotor blade's angle of incidence is the angle between a reference line of the helicopter and the chord line of the rotor blade. Remember that rotor blade angle of incidence may be increased or decreased by the pilot. A variable angle of incidence has a single but extremely important function. It enables the pilot to control his angle of attack, and angle of attack is one of the most important determining factors in producing lift. Angle of attack is the angle between the chord line of the airfoil and the relative wind. To understand relative wind, let's assume that these dots represent particles of air which are not in motion. However, when an airfoil passes through them, a relative motion is produced. This relative motion is commonly termed relative wind. Since this air motion is entirely dependent on the movement of the airfoil, it will always be directly opposite to the direction in which the airfoil is moving. Thus, if the airfoil moves in this direction, the relative wind will be directly opposite. When the airfoil moves in a different direction, the relative wind will also change. Remember that the relative wind is always directly opposite to the movement. Now let's take a look at the similarities between a fixed wing and a rotor blade. Their angle of attack is measured in exactly the same way. On both, it is the angle between the relative wind and the chord line of the airfoil. A small angle of attack results in a small amount of lift. If the angle of attack is increased, the amount of lift increases. The greater the angle of attack, the greater the lift. However, there is a limit to this. At angles greater than about 15 degrees, there is a tendency to stall, and this results in a sharp reduction in lift. As we pointed out earlier, a helicopter pilot varies his lift and achieves control of the helicopter not by varying the RPM of the rotor, but by varying the angle of attack of the rotor blades. By applying collective pitch, he changes the angle of attack equally on all main rotor blades in all positions. Through cyclic control, however, he can increase the angle of attack on one half of the rotor disc and simultaneously decrease it on the opposite half. When this happens in flight, the rotor disc is made to tilt, and the helicopter moves off in the direction in which the disc is tilted. This results in a change of attitude in the helicopter. The aircraft tilts in the same direction as the disc is tilted. Attitude is the angle of the entire aircraft relative to the horizon. This nose-down attitude is characteristic of a helicopter in forward flight. The faster the flight, the lower will be the nose. Stopping quickly results in a change of attitude. This nose high altitude is characteristic of a sudden stop. Lateral motion also changes the attitude of the helicopter. Here, as always, its attitude tilts in the direction of flight. Attitude, then, is the angle of the entire aircraft in relation to the horizon, and it should never be confused with angle of attack. Now let's review some of the more important points of this film. Of the four factors which give you lift, A helicopter pilot can control only two: the angle of attack and the velocity of the airfoil. Since rotor RPM is kept constant, the only way to vary lift is to vary angle of attack. Lift holds you up and also provides horizontal and vertical control. A helicopter's rotor blades perform the same function as an airplane's wings, except that they provide both lift and thrust by rotation. In broad terms, the angle between a reference line of the helicopter and the chord line of the airfoil is called the rotor blade's angle of incidence. A variable angle of incidence enables a pilot to vary his angle of attack. Angle of attack is the angle between the relative wind and the chord line of the airfoil. There are two ways to vary angle of attack. Applying collective pitch changes it equally on all main rotor blades in all positions. By applying cyclic control, lift is increased on one half of the rotor disc, decreased on the other half, and the disc itself is tilted. The helicopter will fly in whatever direction it is tilted. This, of course, results in a change of attitude of the aircraft. The helicopter is capable of many maneuvers once deemed impossible in an aircraft. Knowledge of your rotor blade angles is a solid foundation on which to build a full understanding of the principles of helicopter flight.